right, we're going to take a look at our assignment where we were first introduced to our binomial distribution and then the parts where we compared it to the normal model. And so here we go. First off, we start off with our probability of colorblind, and then we want to know how many do we expect, okay? And so we know how many do you expect, that's the mean. And so we know that our binomial is that n times p, which of course is coming from the formula chart, okay? And I think we know that that kind of makes sense that naturally we see that n times p seems to make sense for our values there. Okay, so here we have that mean for binomial is n times p. All right, with that standard deviation here, the square root of n times p times 1 minus p. All right, so there's that first one. And that computed out then to be 10.4 mils and then with 3.09 as that standard deviation. Okay, now we then get into some actual computing. So we want to talk about the work you need to show and then the answers that you get. So we want to find exactly 5. So that's out of the 130, we want to find exactly 5. So here's the success with 5 successes. Here's the failure rate with then 125 failures, because you know this 125 plus this 5 will total to be that 130. The successes plus the failures is that 130. Now, calculator wise, that's going to be in our binomial PDF. So let's take a look at where you're doing that from second vars. Okay, so here we have second vars. And then we're going to go up to that binomial PDF. PDF is that particular or that exact amount of successes. When we do CDF, then that's going to be an accumulation, and that's in our next lesson. So we want to do binomial PDF, and we had 130 trials. Okay, and then we had our probability of success. The colorblind was that 0.08. And then we wanted 5 successes. So there's our 5. And so if you did not have an updated operating system and you just wrote it out or just had to type it out this way, then we had the 130 and then your comma, of course, is above the 7 and then 0.08 and 5. All right, so that is what then gives us that probability of 0.0279. Now, taking a look at what this looks like, because that's important that we understand what's going on. So here I have this binomial distribution. And so you can see these bars that are discrete, okay? And they're really small because that's n equals 130. Now, remember how we said a moment ago it's centered at 10.4? Well, look here. If I zoom in, then that mean is centered at about 10.4, okay? And then we had that standard deviation of 3.09 or whatever that was. Well, see, look here. Is this bar right here is the 5 men, 5 colorblind men out of the 130. And so then that's the area for that event. Then next we are asked exactly 3 or exactly 4. So we're going to add those two separate binomial PDFs together. So the work you have to show is this. You have to put that in that formula that way to show 130 with 3 successes and 130 with 4 successes. Now, calculator-wise, you do not have to show that work, but here that is what I put in the calculator to come up with that 0.0173 for that portion. Now, let's look at what that's showing me. That is these 2 yellow bars here. So I totaled those together in the next step. So the next step, I guess actually in the next step, we just approximated it with the normal model. So this is interesting, and I've kind of been looking at this this evening because I want to see what is happening actually to make this become close. So what I did was I came here and I said, okay, well, I'm going to let my x's be from 3 to 5. So I found a z-score at 3 and a z-score at 5. So see, that's what's happening. But what's interesting is, see, 3 is technically right down the middle of this here. So, in fact, I've just thought here, let me take a picture. Let me take a picture of what's happening here and show you so I can draw on this, okay? So here we go. If I'm going to, let me see if I can, I don't know if it'll allow me to put that in there, but if I was to put that, let's see if I can insert in that. There we go. So if I was looking at this section, and this is the 3, 4, and 5 successes. So what's interesting though is that really the 3 successes is like right here. I mean, like, so if I normal model this thing from 3 to 5, that's right here. So that's kind of what's happening and why we end up getting a little discrepancy because in order for me to be able to have all of these sections, those 3 bars show up for 3, 4, and 5, on the computer, I actually had to go from, look here, see, I had to go from 2.5 to 5.5 to get those bars for 3, 4, and 5 to show up. So anyway, interesting. You ought to play with this. It's very interesting to kind of see what is actually happening. Um, so so here you can then see if I'm just going from 3 to 5 with this normal model, then I can see how there's going to be a discrepancy there between that overlay of the normal model approximation from 3 to 5. Now, what's interesting, so in fact, let's talk about what that computes out to be. And so here is what that is. There is that one. So that computes out to be when we do the normal model approximation is 3 point or 3.2%. Now, when we totaled those up with the binomial, that was like 4.5%. So we have that discrepancy, 4.5 compared to that 3.2%. And so you can see on this picture why there's a little bit. See, that yellow is a little bit extra. Okay, now what I noticed is whenever I went to this app, and if we looked then at, we let it, see, look here, if we let it compute the normal approximation from 2.5 to 5.5, it got closer. Look at how much closer. It was just a little over 0.5% off. Okay, so that isn't so interesting why that's doing that. Okay, and now another thing, FYI, you can see that as this binomial distribution, as n is getting bigger, then look at how small these and skinny these discrete bars are. And so that when you do the normal approximation, it will be closer to this binomial one than than it was whenever we had a sample size that was really small. So whenever we did this here, then our approximation is not going to be as good and as close then as whenever we had a really large sample size. Look at that. When that sample size is 390, look at how much, look at that. Your normal approximation is probably going to be spot on with that binomial. Okay, so those are interesting things to think about what's happening here. We'll go ahead and finish out this answer then. So here, they're fairly close. As n increases, that binomial and normal model approximations get closer. All right, so let's take a look at this next one. This was the 13% lefties. And so here was your mean and your standard deviation. So now if we do that, this is interesting, at least one. So here I keep throwing in some other things to you so we don't forget those. So to be at least one of the class of 25, that would be 1 minus probability that none of the 25 are lefties. And so then we have 1 minus they're all righties. Okay, now I get into among my 180 students, exactly 20 and 21. So here I'm going to be adding together those PDFs. And then I had exactly 18 or 19. So what ends up happening is I put in here, I kind of built in the accumulation of from 18 to 21. Oh, looky there. I think I see something. See that right there? That's wrong. Is that not supposed to be 20 and 21? Okay, so I need to fix that there. So I can tell those that was supposed to be a 20 and this was supposed to be a 21. Okay, but I think that is the correct probability. Okay, so now if I totaled up from that 18 to 21, here's what I got. 25.37%. So I want to look at that. I love this little app that I found on this website because I want to see what this is looking like. It's just interesting. Okay, so here I'm going to set this to my 180 in my sample size. Okay, and then let's see, our lefties were 13% there. Okay, and then let's see, we wanted from 18 to 21. Now watch what happens though when I put that in there. If I go 18 to 21, then it just shows 3 of these bars. Remember, I have to really like go to 17 and a half to take it to 21 and a half to get all 4 of those bars of the 18 probability of 18, 19, 20, and 21. Okay, so that's those discrete areas. Now, if I do the normal model from that 17 and a half to 21 and a half, which is those things, then see, look at how close that is. It is almost a percentage point off, but that's also probably a bigger discrepancy because we're closer here towards the mean. So we're closer here into the middle of it. But anyway, when I had done my approximation from 18 to 21, that would be a little bit off. So if we were taking a look at this, and we were then going to be computing that, seeing what that looked like exactly. So let's take that and put that a little bit so we can see what's happening and see how that normal is different. Okay, so let's see here. All right, here we have this, and let's zoom out so we can see that better. Okay, see, because what's going to happen then is when we do that normal from 18 to 21, then what's going to happen is we're not going to completely have um, all of that yellow taken care of. So if I was to look at that area from 18 to 21, because see, this is really going from 17 and a half to 21 and a half. So in fact, let me kind of zoom in on that so I can show you that again. See, right here, this was, I need to get right down the middle of that thing because that starts at 17 and a half. Right here, this red line is where it starts at 18. And then it goes up to 21 and a half. So this red line is where I stop at 21, and so on. And so all of this in here is what that normal approximation would be. So you can see a little bit at the little half there to the left and that half there to the right. That is why our computing is a little bit off from our binomial approximation to our normal model approximation. And so here on this one, we were just a little bit off. Let's see. See, I was actually a bit more off on this one than I was on the previous. But anyway, that is what's happening with that relationship between our binomial and our normal. So I wanted you to know how to do those normal probabilities and then see that connection from the binomial to the normal approximation.